Okay, today we're going to look at the practice fourth hour exam, and I'll just start working through problems with you, and we will get as far as we can. All right, the first one says a certain process is carried out at constant pressure. The Q is found to be, Q at constant pressure then is found to be minus 2200 kilojoules. In another experiment, delta E is equal to minus 2190 kilojoules, and delta S is equal to minus 350 joules per Kelvin. Okay, I've got that data transferred over to the pad so we can start working with it. Now we're looking at the relationships between all of these variables, and we were asked to calculate what is the work equal to. So we need to know how all of these things are related. And so Q at constant pressure, that's going to be equal to the delta H for the process, because that's the definition. The heat flow at constant pressure is delta H. Now, delta E is also the heat flow when the volume is held constant. So those relationships hold. And work is defined as minus P delta V. Don't see anywhere we need delta S in this problem, but it's probably there for one of the other problems a little bit later, maybe. I don't know. Okay. The other relationship is the relationship between the enthalpy. Delta H is equal to delta E plus P delta V. H is E plus PV. So if the pressure is going to be held constant, we can pull that out of that relationship, and we use this relationship. The reason why I put it this way is because work is equal to minus P delta V. So that gives me a relationship between delta H is equal to delta E. And if I put the minus sign on the other side, that P delta V is minus work. Okay, so we have the data that we need in order to calculate our answers. Because we know what Q at constant pressure was, delta H. That's minus 2200 kilojoules. And delta E was minus 2190 kilojoules, and minus W. Well, I see minus signs all across there, so I'm going to go through and just multiply through by minus 1. And then I can see if I wanted to get W by itself, I could subtract 2190 from both sides. And that would give me plus 10 kilojoules. And of course, the works cancel is equal to the work. So that would be the answer to this particular problem then, is the work is going to be plus 10 kilojoules. So, all right. Okay. And we see we did get the correct answer. Now looking at the next one, we've got a reaction. And the reaction is 4 NO2s, and 1 O2 goes to 2 N2O5s. And we have delta H of formations for all of the substances, the NO2, the O2, and the N2O5 given at the right. And it says, what is the partial pressure of NO2 in the standard mixture for this reaction? Now, all we need to know is the reaction to answer this question. Remember, the standard mixture for any reaction system is 1 atmosphere pressure for each gas present, 1 mole per liter for each ionic substance dissolved. Now, you have to be careful there. If I'm talking about sodium sulfate, it would dissolve in water to make Na plus and 2 SO4 minus ions. But the standard state would be 1 molar concentration of sodium ion and 1 molar concentration of the sulfate ion. Just like if I've got 4 moles of NO2, like in this particular problem, its pressure is still 1 atmosphere pressure. So we don't need the pad to work this one. The answer is the pressure of each gas is 1 atmosphere pressure. Now, so the correct answer is D. It's 1 atmosphere pressure for the NO2, 1 atmosphere pressure for the O2, and 1 atmosphere pressure for the N2O5. The total pressure would be 3 atmospheres, but that wasn't the question asked. Yeah. All right, let's look down then at number 3. Number 3 is the same reaction, and it asks us to calculate the delta S for this reaction. And we don't have a delta S or the third law entropies of formation given in the table. So the relationship that we're going to need for number 4 is delta G is equal to delta H minus T delta S. And these, so let's go over to our pad. Now I'm going to be using the data that's here. If you've got a copy of the exam, you can follow along with me, but it'll disappear when I start working on the pad. So if I want to get delta S by itself, then I can transfer the T delta S over to the left side and the delta G to the right side, and I would get T delta S is equal to delta H minus delta G. Yes. And so delta S is going to be delta H minus delta G divided by T. So the problem becomes one of calculating delta H and delta G. So looking at my reaction, let's get delta H. Delta H for the reaction. I've left off all my standard states up here, but you know we're all, so far that's what we're talking about. So delta H for a reaction is going to be the sum of the delta H of formation of the products minus the sum of the delta H formation of the reactants. Okay, so let's look at our data. Now, the delta H, the products are N2O5, and the delta H formation of N2O5 is plus 11.3. So this is going to be 11.3 kilojoules. That's the product value. And there's 2 of them, 2 moles. So that represents the heats of formation of the products, or just one. And now I have to subtract off the delta H of formation of the reactants, and we got 4 moles of that. And from the table, NO2 is 31.8 kilojoules. Okay, so this allows us to get the delta H. It's going to be 11.3 times 2. Okay, 11.3 times 2 minus 4 times 31.8. Okay, so what I'm getting here is minus 104.6 kilojoules. Okay, I think I got it right, but I can check the idea on the side. This is an oxidation reaction, which is another word for combustion. If it happens fast, they give off heat. So the sign ought to be negative. I'm pretty confident the sign is correct. I might have done the math wrong, but the sign certainly is correct. Now, let's go to the next part. The next part is to calculate the delta G. And it's the same formula, the delta G of formation of products minus the delta G of formation of reactants. So I can do the same numbers. I have 2 moles of the N2O5, and the delta G column is 115.1. That's 115.1. You know, this webcam reduces everything, so I'll try to start writing a little bit bigger. I need to subtract off 4 times the NO2 value. So I've got 4 moles. The NO2 value under delta G is 51. It's plus 51.31. Now let's do that math. So we got 2 times 115.1 minus 4 times 51.31. 2 times 115.1 minus 4 times 51.31. That looks correct. So I'm getting delta G to be plus 24. Is that right? I'm surprised. 24.96. Okay, so I think I really want to double check those numbers again, just to be sure. 2 times 115.1 minus 4 times 51.31. Yeah, 20 plus 24.96 kilojoules. So now, to go back to what we were going to do, we're going to calculate delta S from delta H minus delta G. So delta S is delta H. We got up here minus 104.6 minus delta, okay, where am I? Yeah, minus delta G, which we get to be, we got delta G to be plus 24.6. They're all in kilojoules. And I need to divide that now by T. So minus 104.6. And just for grins and giggles, I'm going to double check that one too. 2 times 11.3 minus 4 times 31.18 minus 100, no, 11.3 okay, 2 times 11.3 minus 4 times 31.18. Okay, I did find a mistake, but it wasn't the one I expected. 102.12 up here, and it is still negative. So this one should be 102.12.
Dr. Pearson?
Yes.
Okay, before, whenever I wrote this down, I had it written as 11.3 times 2 minus 4 times 31.8.
That's probably what I did. I probably copied it wrong. It should be the table value, if you look at the table, is 11.3 for the delta H formation of N2O5, and it is 31.18 for the NO2. So I think that's the numbers that I did use correctly. I probably hit the 2 instead of the 3 on my calculator. I think that's probably what happened.
But here's my question, because whenever I entered it in the calculator as 2 times 11.3 minus 4 times 31.18, the answer was negative 102.12.
Yes,
But
that's
whenever I entered it in my calculator as 11.3 times 2 minus 4 times 31.8, which is all the same figures, the answer was negative 104.6. So it's just the 11.3 times 2 reversed. Does that make sense?
it's, the correct numbers you should enter on your calculator should be 2 times 11.3 minus 4 times 31 is 31.18. That's what happened a while ago then. Yeah, you spotted it. What I did a while ago is I put in 31.8 like you did there. It's 31.18 is the correct table value.
Okay, all right, I see it.
And then that is correct.
Okay.
So let's go back and fix this number here. It's 102.12. But the thing that was bothering me, and the reason why I kind of jumped on this and was careful, was I expected the signs to be the same between delta G and delta H. Actually, if I could make this reaction work, this would be a great one for something I have in mind for storing solar energy, but that's another story for another day. But you can't really get this, you can't get this clean a reaction when you actually react NO2 with O2. You get a whole bunch of oxides, not just N2O5. But okay, now, so let's put these numbers in. I've got that number, and I want to subtract 24.6 from that. That is 24.96. I almost did it again, 0.96. So I'm taking minus 102.12, and I'm subtracting 24.96 from that. Should be 96 here. And I get that answer. And I want to divide that. That gives me minus 127.08 kilojoules. Now I want to divide that by the temperature. The temperature has to be in degrees Kelvin or kelvins. Okay. Now, what is the temperature? It wasn't given. It's implied in the table. The table values are at 25 degrees Celsius. So that's 298.15. So I'm going to take this number and divide it by 298.15. and I get the delta S should be equal minus 0.426 and a whole bunch of other digits in kilojoules.
Will you move the paper up some so I can see the
But
bottom?
it's in joules up there, so the delta S should be minus 426.2. Yep, that is what I have on my screen in joules per Kelvin for this reaction. Okay, so it took a little longer than it should have, but that is the correct answer. Now, number 4, let's do a share screen so you can see that. Okay, now we're ready to do number 5. And number 5, we're to calculate Kp for the reaction. So number 5 is calculate Kp. Okay, so let's go back and take a look at the pad. Now, what's the relationship between Kp and what we have up in the data? Delta G superscript, now that does need to be the superscript, is equal to minus RT ln of Kp. So that's the relationship that was derived in lecture, and that's what we're going to need to use here. Now we do have delta G calculated, and the delta G was 24.96 kilojoules, and okay, but I know I'm going to have to use R over here, and it's going to be in joules. R is going to be 8.314 joules per mole per Kelvin. Okay? All right, so this is in joules, this is in kilojoules. I want them both in the same. I'm going to do joules on both sides. So I'm going to get 24.96. Kilo is 10 to the third. That's times 10 to the third. That's going to be equal to my minus 8.314. That's R times T is 298.15 times the ln of Kp. Okay, so the ln of Kp is going to be this number divided by that one. So it's going to be 24.96 times 10 to the third divided by minus 8.314 and divided by 298.15. And that'll give me the ln of Kp. So if we do that, we can have 24.96 with an exponent of third. Now I want to divide that by minus 8.314 and divide it by 298.15. And I get the ln of Kp is equal to minus 10.0693 and a whole bunch of other digits. So Kp is going to be e to this power. If I raise anything to the e power, get rid of the ln over here. So it's going to be second function on my calculator, second function, second answer has my number in it. And if I push that, I should get a number. And I do, I get 4.2359, whole bunch of digits, times 10 to the minus fifth. So that should be the correct answer. So let's go over here and take a look. And we do have the correct answer, 4.2. Now, get ready for the next one. It's going to be number 6. And we're looking at an equilibrium. And if you want to increase the concentration of N2O5 at equilibrium, how should you affect the temperature and pressure relative now to the 25 degrees and 1 atmosphere pressure each substance that we have given? Okay, let's look at the reaction. I'll write this down and then we'll go back over to the pad. 4 NO2s. Everything's gaseous, so I'm not going to write this subscripts. It gets too cramped. And we've got 2 N2O5. Okay, let's go back over. Now, so this is a reaction, and we want the effect of temperature, I'm going to say increasing, and pressure, I'm going to say increasing. That maybe is not what this problem is saying, but that's the way I'm always going to solve the problem. I'm going to see what happens if the temperature increases, and then if the temperature is decreasing, then I'll say it's the opposite of what I just figured out. Now, to get the temperature, I need the value of the sign of delta H. Okay, so let's go back. We calculated that way back early. I think it was negative delta H. How did I calculate it? Delta H is minus 102.12. All I need to know is the sign. If it's negative, it means heat is coming out. So heat, it's like heat is a product. Okay, now pressure depends on the pressure. If I increase the pressure, that shifts to fewer moles. So I'm going to look at increasing pressure. Increasing temperature is going to shift the reaction to the left. Increasing pressure is going to shift the reaction to the right because there's 5 moles of gas on the left and only 2 on the right. So this is the effect that increasing temperature and pressure would have on this reaction. But the problem says, suppose I want to increase the amount of stuff. So I want to shift it to the right. So if I want to shift it to the right, it means increasing temperature shifts it left, so I want to decrease the temperature and increase the pressure. Pressure shifts it to the right. So these are the things that I want to do in the reaction. So increase the pressure and decrease the temperature is what we want to do if we want to get this reaction optimized by temperature and pressure. And of course, we're talking about relative to the data we had or we used from the table. But it would be the same effect regardless of the starting temperature and pressure. Whatever the starting temperature and pressure is, if you increase the temperature further, it'll shift left. or if you increase the pressure further, it'll shift right. And we're talking about compressing everything. Okay, so let's go down to number 7. And number 7, we want delta G for a mixture. Okay, that's other than the standard mixture. So the let's go over to the pad. The relationship we want is that the delta G without the superscript is equal to delta G with the superscript plus RT ln of Q. Now, Q is expressed like the equilibrium constant is. We've got our reaction still up here, so we want the pressure of the N2O5. So delta G is going to be delta G superscript, and we calculate, what was it, 24 point something? 24.96 kilojoules. I'm going to anticipate the R there and make that times 10 to the third. Now, R again is 8.314. And temperature is 298. And now I have to get the ln of Q. Now what's Q? Q is going to be, that's going to be the ln. Now, it's going to be the pressure of the N2O5, P of N2O5, and that's going to be squared. And I want to divide it by the pressure of the NO2, and that's going to be to the 4th power, times the pressure of the O2, and that's going to be to the 1st power. So let's go ahead and do that part of the calculation. We're told in the problem the pressure of the well, actually the pressure is going to be the balancing coefficient pressure. So the pressure, that's going to be the log of the pressure of NO2 is 2 atmospheres, and it's squared. The 2 is given in the problem. The square is for the balancing coefficient. Pressure of NO is 4, and that's going to be to the 4th power. And oxygen is 1 atmosphere to the 1 power, okay? So I've got 2 squared divided by 4 to the 4. Okay, so let's do that. 2 squared divided by 4 up arrow 4. No. 2 squared divided by 4 up arrow 4. Okay? Now, I'm coming out with this part right here being 0, 1, 5, 6, 2, 5. Now I want to take the log of that, ln of that answer. And what I get for this part right here now is minus 4.15 and a whole bunch of digits. So now I want to multiply that by T, multiply it by R, and add this to it. So I'm going to multiply it by times 298.15 times R is 8.314 is that. And then I want to add to that 24.96 with an exponent of third. So if I've not screwed it up somehow or other, then I get delta G is going to be equal to 14654 and some decimals. And now this is in joules. I'm sure the answer is going to be in kilojoules. Yeah. So I divide by 1,000, so I get 146.5 kilojoules. Okay, so that should be okay. And if we go back to our screen, okay, so KP, yes, wait, I got 14.6. Let me look at my screen. It is 14.6. I divided by 1,000, but it only moves the decimal point 2 places. So it is 14.6. That's correct. I guess I really ought to round 14.654. I should have rounded that up one, but still okay, plus or minus 1. Now, so looking now at our next problem, we want to get the Kp for that, or the equilibrium constant for that reaction at 10 degrees. So I want the Kp at 10 degrees Celsius. Yes, okay, for the reaction. So this is number 8. So let's go back, and we're working with the same reaction. And I usually try to do that so that you don't have to keep redoing the same thing over and over again. Saves us time on the exams. The relationship, though, is delta G superscript is equal to RT ln of Kp. So if I knew delta G at, and now what I want in here is 10 degrees Celsius, that's going to be 283.15 Kelvin. So I need the delta G at that temperature, not the delta G at the table. Now remember how we do that. Delta G is equal to delta H minus T delta S. Got superscripts here for everything. Yeah. And now we've already calculated delta S and delta H. So the delta H we got was minus 1, where was it? 102.12. And that's in kilojoules. This is going to be joules per Kelvin. So I'm going to multiply that times 10 to the third. So we're consistent again. Minus the temperature. Now the new temperature that I want is 283.15, I guess. And then times the delta S value. The delta S value, we calculated it earlier also. It's 420, it's minus 426.2 joules per Kelvin. So I want to, now you want to be really, really careful. That minus times that minus is going to make this plus. So this last term is going to be positive. The first term is going to be negative. So the way I'm going to do the math is I'm going to do the last part and then subtract off the 102. That just saves me math steps. Okay, so I've got 426.2 times 283.15 0.15. So now that should be, remember, I'm going to take that minus times that minus gives me a plus term. So I entered them positively on the test, on the calculator. And then I want to subtract 102.12 from that. And what I came out with is delta G superscript is 102. I did it again. 120,576.41. That's in joules. Okay, is equal to minus R, 8.314. Temperature is 283.15. And ln of Kp. Okay, so I can take this number and divide by this number, divide it by minus 8.314 and divide it by 283.15, and I get this number. Wow, that's a really, really tiny number. That's got to be wrong. I'll run it on through, but that doesn't look good. I get the ln of Kp to be minus 51.23. I know that's way too big. Let me see where I made the mistake. I did enter that in joules per Kelvin, minus 426.2. That is what I got. 102.12. Oh, did I? Oh, well, I know what I did. No, I didn't. That's right. That is delta H. And it was 102. Minus 102.3 times 10 to the third. Okay. Okay, so minus for the formula and minus from delta H is positive. So let me redo the numbers. 426.2 times 283.15 is that number. Minus 102.12 that is the number I'm seeing. Divide that by 8.314 and divide it by 298.15. No, 288. 283. 10 degrees, yes, 283. 283.15. That's right. Times this is that number, minus 102.15 is this. And it looks like I've come up essentially the same number again. But I'm not getting one of my answers, that's for sure. So Kp is 5.7 times 10 to the minus 23. That's why I said this doesn't look like a real number. Okay. delta H was minus, I don't think I copied those numbers, minus 102.12 times 10 to the third, that's delta G to delta H, minus T is 283.15, and delta S was minus 426.2. Okay. $283.15 times 426.2 minus 102.12 with an exponent of 3. I get delta G is plus 18558.53, and that's equal to R is 8.314 times 283.15 times the ln of Kp. So I take that number divided by 8.314 divided by 298. No, I keep doing that again. 283.15. And I get, now that looks like a better number. I don't know what I did up there, but this looks more like a correct number. I get ln of Kp to be equal to I forgot to divide it by. Oh, I didn't. Delta G superscript originally was plus, and it's still coming out plus, and making sense. And so this should be minus 7.883. And then e to the second is 3 point. Yeah, that's right. Kp is 3 point. I'm getting 8 times 10 to the minus 4. Okay. Well, this part of the math below the line is correct and checks out, so we should be okay. All right. Lots longer than that should have taken. But it is pretty easy to make a sign mistake. And you always want to make, the reason why I knew I made a mistake was I was coming out with numbers way too big. And I was coming out with one time a equilibrium constant that was too small. It was a negative number, so it didn't work out right. Okay, all right. Let's look at the next one. Maybe this will go a little smoother. Okay, this is a balanced equation. So I'll copy the equation now, and it's CR CL3, and reacting that with MN O4 minus permanganate, and we're going to make CrO4 2 minus chromate and MnO2 and ClO4 minus. Okay, and we're going to do it in base. Okay, so let's go over to the pad, and this will probably finish up the lecture time that we have for today, but I'll work further and at least do about half of it before I stop. Okay, first thing we want to do is we want to pair together the things that are going to be in the two half reactions. Now, chromium is in both of these two. No, it's not. Yes, it is. CrCl3 is in chromium, and chlorine are in these two, and manganese is in these two. So I'm going to start CrCl3. I'm going to take that to CrO4. That should be 2 minus. Yeah, it is. Okay. I copied it wrong up there. Oh, I didn't. I just got lost in the oxygen. And the other product is ClO4. Okay, now what we have to do is first balance the atoms that aren't oxygen or hydrogen. Well, chromium is already balanced there. Chlorine is not. So I need 3 chlorines or 3 perchlorate ions to balance chlorine. So now chlorine is balanced. On this, we've got 3 times 4 is 12, and 4 more is 16 oxygens. So I need to add 16 waters to this side. And when I do that, I've got to add hydrogen ions to the opposite side, and 16 times 2, so I'm going to need 32 H pluses. And now let's see if I can get the charge. I've got minus 2, minus 3, so 16 times 2 is 32, 32 H pluses. And so I've got 32 minus perchlorates minus 1 and minus 2. So I've got 29 positive charges, so I need to add 29 electrons to this. So let's see if I can write this where it's a little bit better. We've got 16 H2s, O, plus a CrCl3, negative, and that's not negative, that's 0. We're going to CrO4, 2 minus, and 3 ClO4 minuses, and 32 H plus, and 29 electrons. Okay, wow, biggie. Now let's do the permanganate to manganese 4 oxide. So we get MnO4 minus going to MnO2, and manganese is balanced. 4 oxygens here and 2 there, so I need 2 waters here. And now I've got oxygen balance. I've got 4 hydrogens on this side, so I need to add 4 H plus ions to this side. And that gets me that. And I need the charge to balance, so I need 3 electrons here. because 4 plus 4 and plus 3 plus 1 is -4. These are 0 on this side. So this is good. And now I've got 3 electrons on the left and 29 electrons on the right. Just to be sure that is balanced. Yes. 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 16 oxygens, that's right. And then I've got 32 and 29 is going to be 3. That's not balanced. I got 32 positives and I forgot my 3, I'll bet you. 3 negatives and 2 is 5. That's 27. And not 29, that's 27. Oh, that's good. Because to make the electrons gain and lost, I just need to multiply this last through equation through by 9, right? 3 times 9 is 27. So I need to multiply this one through by 9. So when I do that, I'm going to have 9 times 4 times 9 is 36 H pluses. And now 27 electrons and 9 MnO4 minuses going to go to 9 MnO2s and 18 H2O. Okay, I'm going to double check and be sure. 2 times 18 is 36 hydrogen balances. 9 manganese, 9 manganese. 4 times 9 is 36. So I've got 18 and 18 oxygens. My net charge on the right is 0. So 9. So I need 36 minus 27 minus 9. That's right. Okay, so I'm pretty confident this is one of my half reactions. And this is my other half reaction. That would have been 27 also there. No, I've got it down here, 27. Okay, all right. Now the number of electrons in this one and the number of electrons in this one will cancel. So I can take those off. So let's try to put all of this stuff together. You know, I must switch and get another piece of paper and do landscape orientation. So we get ourselves some lighting. Okay, so let's copy everything that we've got on the 2. So I've got 6 waters from here, 16 waters. Yes, I've got 16 waters. I still have CrCl3, and that's everything to the left of the arrow there. I'm going to add to that 36 H pluses. And 9 MnO4s. And now that's going to go to what I've got on the right up here is a CrO4, 2 minus, and 3 ClO4 minuses, and 32 H pluses, and the 27 electrons I've already canceled. I didn't include them on the top. They're the same on the bottom, so I won't include them here either. All right, so that takes care of this reaction. I have 9 MnO2s and 18 H2Os. Okay, well, all right, let's see. So I've got 16 waters on the left and 18 waters on the right. So that's going to wind up with 16. That's going to leave 2 waters over here on the product side. Now I've got 36 hydrogen ions here and 32. So that's going to leave 4 hydrogen ions on this side. So now I've taken care of the hydrogen ions and the water. And now I just need to include the other stuff. So I've got Cr, Cl3, 36H plus, I've already taken care of that. I've got and 9 O4 minuses. And we're going, that's everything is left, right? I've got the waters disappeared off the reactant side. Got 4 hydrogen ions, CrCl3, 9 of these. Oops, I forgot. I've got to put my chromium in there. And CrO4, 2 minus. No, that's on. Forget that. That's on the product side. All right. Now let's get. That should be everything that I've got for the reactants. Let's put the products in. The products are going to be the CrO4, 2 minus, the 3 ClO4 minuses, and the 9 MnO2s, and I've already taken in the 2 waters. Okay, now let's just see if we can count up and see if we got everything accounted for. I've got 4 hydrogen ions, 4 hydrogen atoms on the products and 4 on the reactants, so that looks good. I've got 1 chromium in the reactants and 1 chromium in the products. I've got 3 chlorines in the reactants and 3 in the products. I've got 9 manganese in the reactants. I've got 36 oxygens in the reactants. So let's see, right? 4 times 9 would be 36. So I've got 4 oxygens from here. I've got 12 oxygens from here and 18 oxygens from here and 2 more from here. So I have 34 and let's see, did I get them right? 4 and 12 and 18 and 2. So 4 plus 12 plus 18 plus 2 is 36, and that's what I have. So this looks like it balances. I need to check the charge. So I've got a net charge on the left-hand side of this. I've got 9 MnO4 minuses and 4 positives. So I've got 5 minus on the reactant side, and I've got 2 minus and 3 minus is 5 minus. Okay, I'm confident this equation now balances in acidic solution. So if I want to make this go to basic solution, what I'm going to do is add 4 OH minuses to both sides. And when I do that, these 4 OHs, and this makes 4 waters over on the left. On the right, I had 2 waters. So these 2 waters will be gone, and that leaves 2 waters over here. And 4 hydroxides in the product. And the correct answer is 4 OH minuses in the product. Okay, all right. If any of you have to leave, we're a little bit over time now, but I'll continue with this. But the reaction did work. We got it balanced, and so we're okay there. Okay, let's look at the next one, and I'll continue to work for another 20 to 25 minutes, and then wherever I've got to, I'll have to stop there. The videos get too long. It takes too long to translate them, and then I don't want to leave them up there. I'd rather it be of one setting for you than to be one you'd have to start and stop over and over again, although that's probably what most people do. All right, number 10. All right, so we want to know the mass. Let's go back over where you can see the questions in case you don't have them with you. All right, so number 10, what mass of chromium, how many grams of chromium can be plated from a solution of, it's 3.5 molar chromium chloride, chromium 3 chloride, in 1.5 hours by current of 1.5 amps. Okay, I think we got the data that we need. Okay, now we're going to take chromium, and in this compound it's +3. We're going to take 3 electrons, 3 moles of electrons, to make chromium solid. Of course, this is aqueous. It'll take 3 moles of electrons. So I want to know how many grams of chromium will I get? Well, we're going to need the atomic weight of chromium, and chromium is right there. It's 52. So 1 mole of that would be 52.00 grams. So if I had 3 moles of electrons, I would get 52 grams. The equation is showing 3 moles. Now, there's 96,500 coulombs, amp seconds, in 1 mole. So this becomes our rebalancing factor. So I want to know how many grams of chromium. So I'm going to take 96,500 amp seconds, or coulombs, is 1 mole of electrons. And now the number of amps times seconds. So coulombs is amps times seconds. So the current is going to be 1.25 amps. Now, but we're going to put in the time now. The time is 1.5 hours. But we have to have it amp seconds. So the the number of amp seconds. This is go to hours, goes to minutes. There's 60 of those in one of those. And now we have to take it from minutes to seconds. And there's 60 of those. So 1.25 times 1.5 times 60 times 60 is the number of coulombs that we have. So we got 1.25 times 1.5 times 60 times 60. So we're going to have 6750 amp seconds or coulombs. So the number of coulombs or the number of moles of electrons, there's 96,500 of those in coulombs in 1 mole of electrons. So I need to divide that by 96,500. So I've got that number, divide 96,500, and I get my moles of electrons is going to be 0.0, essentially it's 0.07. It's 0.066, 0.069948 and a whole bunch of digits. So that's the number of moles of electrons. So now let's go back to our equation. 3 moles of electrons is going to give us 52.00 grams. Now, how many moles of electrons do we have? So on our balanced equation, it's showing 3 moles of electrons. Our problem amount was the 0.0699. If we divide that out, that becomes our rebalancing factor. It's going to be this number divided by 3. And that's 0.02332. And I need to multiply that to get my answer, multiply the rebalancing factor times 52, the amount shown in the problem. So I'll multiply that by 52 grams. And I get 1.21 grams. Okay, so that should be the correct answer. And it is, there it is. All right, let's move right along. Number 11. Write the following. That should be order, not order. Order of increasing entropy. Okay, so if you're thinking about entropy or disorder, we're looking to see which of those would contain the most entropy. So the molecules that we have are CH4, CHCl3, CH3Cl, and CH3OH. Okay, now we want to get the increasing entropy. Entropy is disorder. So the first thing we're going to look at is the total number of atoms that we've got in the molecule. So in this case, we've got 5 atoms, and we know the structure really if we needed it. Remember, it's going to look like that. It's going to be a carbon here and hydrogen, hydrogen and hydrogen and hydrogen. And then we're going to have this one. It's also got 5 atoms in the molecule, and it's sort of similarly shaped. We've got 1 hydrogen here, and chlorine, chlorine, and chlorine here. CH3Cl, it's still got 5 atoms, and we've got the same basic shape. We've got a carbon here, we've got 1 chlorine, and hydrogens in the other places. And then we've got CH3OH, and that's sort of based on that structure, but it's a little different. It's like this. Carbons here, hydrogen and hydrogen and hydrogen. But we got 3, 4, 5, 6. So this has got 6 atoms in it. So I'm going to bet that this one is the greatest. It's got more atoms to rearrange in space than these do. So I'm going to pick that one as the best answer. And you know what? Play the test. There's only one answer that's got number 4 in the correct place. So I'm done. I don't have to do any of the others. But let's just see why this one is the smallest. It's always easiest to put the largest and the smallest. I would have guessed this one smallest. All of these other 3 have 5 atoms in them, but this one is the smallest molecule and most complex. Hydrogen atoms are smaller than chlorine atoms and so forth, and they're much lighter. So I'm going to guess that this is going to be the smallest. And then when I look at these, I'm going to say, okay, now comparing these two, this one has more hydrogens. It has 3 hydrogens and 1 chlorine. This one has 3 chlorines and 1 hydrogen. That one ought to be next. And then this one should be last. But the key is pick out the 2 extremes first. You want to pick out the 2 extremes first. They're the easiest ones to do. And then when I pick this one first, I'm going to look and see which answers I can eliminate. And it turns out I could eliminate them all. So be wise and play the test. Okay, let's look at the next one. Okay, and now number 12 says, which of the following has the largest increase in entropy? Now, let's remember what entropy is about. It's about disorder. And the more particles, more molecules you have, the more disorder you have, the higher the entropy is going to be. So if I'm looking at reactions and I think, okay, well, these are all gases, but on this one here, I've got 10 moles of gas. Over here, I've got 11. So I'm going from 11 moles of gas to 10. That's a decrease in entropy. So it's certainly not that one. If I go here, I've got 1 mole. It's the same thing. I've got 3 moles of gas going to 1. It is gaseous. Always check. Always check the water, especially. We did. And then we're looking at the next one. The next one, I have the CO2. It's going to be the same sort of thing. 3 moles going to 2. Well, it's got to be this one then. And it is right, because I've got 2 moles of gas here. I've got 1 mole of gas here. Carbon is a solid. So the only one that has an increase in entropy is D. And it is fairly easy to say. So you're looking at the change in entropy is determined by the change in the number of moles of gas, primarily, because gases are so much bigger in entropy than liquids or solids. Okay. Okay. At 627 degrees, the equilibrium constant for a reaction And it's two SO2s, and O2 goes to two SO3s. And we said Kp is equal to 14. Calculate delta G without the superscript at the same temperature when the pressure is equal to 0.001 pressure of SO2. The pressure of the O2 is 0.20, and the pressure of the SO3 is 0.0001. And we want to get delta G without the superscript. Okay, let's go over to the pad and let's see. Now, delta G without the superscript. Delta G without the superscript is delta G with the superscript plus RT ln of K, Kp in this case. Okay, so that's the relationship. The other one we need is delta G with the superscript. I'm sorry, this should be Qp. Delta G with the superscript is minus RT ln of Kp. Okay, so I can plug these things in. I get delta G is equal to minus RT ln of Kp. That's plugging in here. Plus RT ln of Q. And let's do some math because we've got some things we can do. If I'm going to take RT out of all of them, and then I'm going to do minus the log of Kp plus the log of Q. So I'm going to take the log of this minus the log of this. That's the same thing as the log of the ratio. RT times the ln of Q divided by K. Okay, so all I got to do is do my plugins now. I can get Q. Q, maybe I'll set it up right over here. Q is going to be equal to the pressure of the SO3 squared. So it's 0.0001. I want to be sure I did that right. Yep. Squared. And I want to divide it by the pressure of the SO2 is 0.001. And that's right. And there's two of them, so that's squared also. And the pressure of the O2 is 0.2. And that's just to the first power. So let's see if we can do this. And we get 0.0001 squared divided by 0.001 squared and divided by 0.2. Now, I didn't make some kind of mistake. This Q value is 0.05. And K, we were told, was 14. Okay. So 0.05 divided by 14 should give us the this part here. So I want to take this part times R times T. Now the temperature, we got to be a little careful. 627 and 273. That's going to be 900 kelvins. So I want to take the 900 kelvins times the Ln of the number that I have on my screen. So I want to take the Ln of that answer, and I get minus 5.63 times the temperature times 900 times 8.314. And if I'm getting my delta G is minus 42162, and that's going to be in joules. So if I divide that by 1,000 to get in kilojoules, I get minus 42.2. Okay, and that should be our correct answer. And there we go. Okay, maybe I'll do a couple more. Certain reaction at 25 degrees Celsius, AA plus BB goes to CC plus DD at a certain set of pressures for all the components, not 1 atmosphere. Which function below determines the work for the that reaction can do? Okay, now that's just sort of a given. The free energy function, delta G, is the work function. So it's just a simple, do you know which function is related to work? It's delta G. Okay. See about number 15 and see if that's good. Now, got the same reaction. Which function below determines whether heat is given off at constant pressure? The definition of delta H is Q at constant pressure. So that one is easy. Number 16, which function below determines whether order increases or decreases? That's delta S. Those were intended to be gifts, okay? All right. All right, I think I'll stop right there. The next one is going to be a rather involved calculation, and it'll take a little bit of time to set it up. If I get some time later on today, I'll do that, but I'll put these first 16 up on D2L as soon as I process them through YouTube. So let's go here. We're going to stop the recording now.